If I have seen further, it is by standing on the shoulders of giants. Source links in the description below.
Okay, so here we have it. Just as a bonus and as a comparison, this is the acceleration structure in action. We're doing, we have 1024 spheres, 4 reflections, 4 samples. Doesn't look that great, but the fact that we can handle this much at this resolution, let me pop up footage from the pure CPU attempt. And hopefully you can see that this is an improvement. It's actually, like, I wouldn't mind a game that was a little bit like this. And plus, I mean, anyway, the point isn't that we're going to have a pure ray tracing 1000. No game scene has 1024 things in it. Anyway, so just to do the same test that we did in the last video, if we look away, we can see the resolution adjusting as the frame rate does things. Yeah. Anyway, so I think this is pretty cool. Honestly, this is pretty nice. Okay, cheers. Hello, Andrew here, Get Into Game Dev. I have a confession, and that is I am addicted to ray tracing. I know that's a little weird. Sounds weird to me, definitely sounds weird to other people when I tell them. But yeah, I'm busy with things at the moment. I have things I should be doing. But at one point I just decided to Google, is there a way to make a ray tracing acceleration structure which works on the GPU? And unfortunately for me,
I go the extra mile. You and me, we're done. Hey. We're done when I say we're done.
turns out there is. Okay, so let's say that we have a tree structure of some sort where a circle represents an internal node and a square represents an external node, so something which has primitives in it which we can go ahead and render. Okay, so this is the bounding volume hierarchy which we want to render. The issue is, how do we write an algorithm which traverses this and can potentially prune parts off the tree, so not render, not search certain parts, and yet does not use recursion? The thing is, GPUs, they hate recursion. So it turns out the solution is pretty straightforward. What I'll do first of all is I'll just label each node with an index, and this will be in a depth first search manner. So we go down here and then we look at the next child, something like that. Now each node is also going to store the index of the node which we should check based on the result of each thing. So we'll put green and we'll say, where should we go if we trace node 0 and we intersect it? Okay, well then let's keep going. Let's search node 1. Then we hit node 1. If we intersect that successfully, where should we search next? Let's search node 2. Okay, now after we hit node 2, we're not done because we could have other things. So we then search node 3. If node 3 has been hit, we search node 4. If node 4 has been hit, we search node 5. If node 5 has been hit, everything here has been hit successfully, we then look at the next child which hasn't been searched. and continue the process on and on and on. Okay. So, in the worst possible scenario, we are somehow hitting everything. This is, I don't know, imagine that we're looking down a line of spheres and they are all in our range of visibility. Okay, so this is where the interesting bit comes in. These have all got indices. Now let's say that we have a index which represents total failure. Okay, so we'll give it a nice sensible value like -1. Okay, so if we go to the root node and we shoot a ray at it and we miss, we'll then go to the failure state. And the failure state is just some state where the loop will just keep continuing on and on and on and just run its course without doing any extra computation. So see, if we shoot at the root node and then we fail, then we have effectively we skip searching the whole tree. Now, if we go to root node 1 and we fail, well, then we'll search node 6. And so this whole left half of the tree is skipped. Now, similarly, if we go to node 2 and we fail, then search node 3. If node 3 fails, well, then we're not going to search 4 and 5. We'll skip over to 6. So the way this construction goes is actually fairly straightforward. So for a success, if the node is internal, then the success node is its left child. If the node is external, then the success node is the right child of its parent. And we can see here, if the node is external and it is the right child, well then let's say that right child function is recursive. And we can do this on the CPU, by the way. We're constructing it ahead of time. So we go up to node 3, we say, hey, node 3, what's your right child? It says, it's you. So it looks at its parent and says, hey, I'm node 3, what's your right child? And node 1 says, it's you. Okay, so then you know what I mean. You know what I mean. So just for the sake of completeness, I'll finish off this tree. We can see here on node 6, if we've tried node 6 and that's failed, well then, nothing. We're done. And similarly, if we try node 10 and we fail, well then clearly we just didn't hit anything. That's okay. So with this data structure, as you can see, it's using skips without recursion to miss off whole sections of the tree. The next thing that I'm looking at is I'm revisiting the concept of the bounding volume hierarchy. Now, before what I did, technically it wasn't a bounding volume hierarchy for the reason that the volume simply didn't bound the objects. It was space partitioning, which, as some people noted, is better than nothing, but there's an issue. So imagine, by the way, I also decided to switch to an algorithm where we're splitting the space in 2 rather than 8, because it turns out there wasn't that much benefit to it. Keep it simple, 2 is good. So imagine that I want to cut this space in half along the width, along the length. Now, if I shoot a ray at it, this ray is going to successfully intersect in this space here. And that's a problem because then the algorithm will think that we've had success when actually we haven't, right? Because then what it'll do is it successfully intercepts the space and then we test again against this sphere, but surely we should know ahead of time that we're not going to hit this. So what we should do is instead tightly pack the volume to the object, and then that is much easier to check, right? So we shoot our ray, we miss the space, and we know that we missed the space. And there's another thing to mention, and that is a heuristic which I'm using to construct the bounding volume hierarchy called the surface area heuristic. So imagine, for instance, that this thing is here, and then we want to make a bounding volume which includes these two spheres, They do enlarge it a little bit, but it's just at what's necessary and can be easily computed. So the question is, what is the proportion, what is the percentage, the probability that a ray will successfully hit this box? Well, it's roughly given by the surface area of the volume. How about this one? Well, it's again roughly given by the surface area of the volume. Now, every time the ray successfully hits a box, there's a cost because it then has to test the inner objects. So we could say, how many times will this cost be incurred? Well, it's got a certain surface area, which is the proportion, the chance of hitting it, and then it's got two objects in it. So what we have is the cost is, we have a left and a right child, I guess. It's the surface area of the left times the number of objects in the left plus the surface area of the right times the number of objects in the right. So in this case, surface area of this times 1 plus surface area of this times 2. Now, when we come to constructing the bounding volume hierarchy, we want to basically enumerate through all the possible combinations of bounding volumes and see which combination minimizes the function. So this would probably be a really bad partition to make. We could go with something like this. This actually looks like quite a good partitioning. And we also have the possibility of not splitting at all. So if we imagine this is the original state that we were in and we wanted to subdivide that space, we would compare the current best cost value to the parent's cost value, because we still have information about the parent before we decide to split it, so we can evaluate the function, and this gives us more control of our bounding volume hierarchy creation. Now, writing a recursive algorithm and debugging it is hard, and that's just when it's on the CPU. So I decided to focus on the CPU implementation of the algorithm, plus a few extras. Why not? Okay, so before we implement the algorithm on the GPU, we need to get working code going, which I did. Let's have a look at how that compares to previous results. So previously, I was just straight up busting out every trick in the book. We had multi-threading, we had SIMD, and yeah, it was what it was. So what were those results? Side note, back in the early days of making these benchmarks, I accidentally wrote 9192 instead of 8192. I know. I'm just going to have to live with it. So there we have it. It's actually not that bad, at least from first appearances. So if we have about 9,000 spheres and we're shooting 32 samples per pixel and we're shooting up to 32 bounces, I mean, yeah, we'd expect the render time to be pretty bad, but it's about 29 seconds. So we re-implement it with the new acceleration structure. This already had an acceleration structure, but we're just rejigging it with the surface area heuristic and a bunch of other wizardry. So how does that go? Okay, so that's pretty good. That's a big improvement. Now, we can also just look at how is the GPU performing by itself. So unfortunately, there are some limitations. Now, just make this a little more visible by scaling that back. Just with my implementation, it only really worked on up to 1024 spheres. That had to do with the data structure that I was working with. But yeah, if we look at this, we see that the GPU, of course, it has a lot of power. It starts off insanely powerful, but it's on a really bad growth curve. So, like, it's not good. So with that working, I moved on to the GPU implementation. Now, just a note on some of the limitations. The way that I'm passing data to the GPU is by textures. So send through a row of pixels, and the numbers in those color channels represent the parameters of the sphere or the bounding box node or something. There's a limit on that. There's a limit on the pixel dimension that the graphics card can accept. Now, there are ways to get around that. So I more or less found that I was limited to 1024 rows of pixels. Now, I can get around that by passing in like a 500 by 500 image. That's perfectly fine. But the math to work out the exact offsets and things, it didn't feel like it was worth it to me at the time, because ultimately I'm going to run over to C++, where I can use structs and shader storage buffer objects, which have arbitrary size limits and don't involve me mucking around with pixel coordinates and things. This brings me to my second limitation, is that this implementation is in Python. Now, that shouldn't affect the timing too much, because the portion of the rendering that I'm timing is just a call to a compute shader, and that is roughly independent of the implementation language, as you can see coming up in the timings. Okay, so how did the GPU perform after we added that acceleration structure? Well, here are the results. So it is worth noting that some of the performance of the acceleration structure is random. It has to do with the distribution of spheres, and in my Python implementation, unlike my C++ implementation, the random number isn't seeded, so it will be slightly different performance each time, and if I walked around, that frame rate would modify as well. But it's pretty good. The gray line is, again, just the raw GPU with no acceleration structure. See, it starts out incredibly fast, but pretty quickly it becomes less powerful, whereas this yellow one is the GPU plus the acceleration structure. So hopefully this is demonstrating that it's possible to add acceleration structures, and they matter. They make a difference. So here we are rendering on 1024 spheres. Performance has dipped a little bit because I switched OBS on, but I mean, the fact that we can render this much with 32 samples and 32 bounces, this is much more than we would use in a real-time application, and it's handling it. And it's handling it better than the C++. I mean, not phenomenally better, but that also comes down to the implementation. So yeah, that's pretty cool. That is pretty cool. So there we have it. Those are our results. Now, you may note that the fundamental growth curve of the GPU implementation is kind of the same as the CPU implementation. It's just that the GPU is the growth curve is shifted down, is all squashed down. That's actually good. That means that the GPU is performing as efficiently as an optimized CPU. The only difference is it's squashed down because it's parallelizing it over a lot more cores. In all cases, the render time appears to be sublinear, that is sublinear to the number of spheres. So as I double the number of spheres, the render time less than doubles. I'm pretty happy with that. There are, of course, an endless number of little tweaks that I could do. One, of course, is that I should probably bite the bullet and port the whole thing over to C++. As a rule of thumb, if a task is taking a little bit of time to perform in C++, it's actually going to take a lot more time in Python, and that's what I found in the bounding volume hierarchy construction. It's a big task. I'm probably going to have to improve the noise function as well. At the moment, I'm just sending over a texture to sample the noise from. It doesn't actually look that good, so I'm going to look at that. And then the other one is in the bounding volume hierarchy traversal. There, in my research, I came across another method where we order it based on which direction we want to step through the BVH in, if we want to step through in the positive X, negative X direction, and so on. And that comes down to building 6 different reordered versions of the same tree according to various dimensions, and then selecting the tree that we want to traverse on the shader based on the dominant direction of the ray. So if the component with largest magnitude is the Y, and that component has a negative direction, for instance, then select the negative Y tree and traverse that, and hopefully that improves the render time even more. But anyway, that's it for me. Thank you for watching. I hope you enjoyed, and I'll see you again soon. Bye.